tech tip video, we'll take a look at how using a reduced order model from SimCenter Flowtherm can allow the accuracy of 3D to be gained in the timescales of 1D. Here is a PCB which is cooled via a cold plate at the back. This cold plate can be connected to the cooling loop in a number of ways. Most configurations will need a number of PCBs, so what is the best way to arrange these in the cooling circuit? Doing this in 3D would be far too computationally expensive, so let's take a look at using a reduced order model for this and importing it into a 1D tool. The Flowtherm model has been solved, and under a low load of 35 watts, the chip temperature gets to 50 degrees Celsius at its highest. Flowing through the cold plate is 35 degree coolant, which works its way through, removing heat away from the PCB. Using SimCenter Flowtherm, these BCI ROMs can be exported and read into SimCenter Flowmaster. The model has been imported as an FMI component and is connected to a thermal bridge which represents the cold plate path. The average heat and calculated heat transfer coefficient is passed to the ROM, and then a heat flow rate is passed back and input into the thermal bridge. All of the electrical powers have been added as input features in Flowmaster. The simulation can be run and the fluid flow visualized much like in 3D. Monitor point data has been exposed as results from the BCI ROM and allows the internal solid temperatures within to be inspected in Flowmaster. Comparing a 100-second heat up scenario, the results give good agreement and show that the imported BCI ROM can give the accuracy of 3D, but with the solution time of 1D. Eight cards need to be connected into the cooling loop and will run at a full load of 70 watts. The temperature cannot exceed 80 degrees Celsius in the PCB, and these will be retrofitted into an existing cooling loop so the design of the loop cannot change. The first arrangement has 2 fluid paths and 4 PCBs in each of these. The flow rate in the 2 lines will be relatively equal, but will the extra pipework reduce the flow rate of the pump? In the parallel arrangement, each line will have access to the coolant directly from the pump. In this case, there will be even more pipework of a smaller diameter, and will this reduce the flow rate even more? In series, the PCBs will have access to the highest flow. However, will the compounding of this take the maximum over 80 degrees Celsius? In arrangement 1, we can see the solution running and the results visualized as the simulation is run. As the system heats up, we can see the hot fluid moving around the system and the temperature in the reservoir increasing. The maximum temperature the fluid gets to is just under 80 degrees Celsius at 1000 seconds. When arranged in series, the temperature increases by a small amount across each, but the combined effect leaves the last PCB the hottest, at just over 80 degrees Celsius, rendering the design non-feasible. When arranged in parallel, the temperatures are the lowest, but this will require extra pipework to complete, as each will have to be plumbed into the cooling loop separately. This design shows that the parallel arrangement gives the coolest temperatures across the 8 PCBs. Running this kind of simulation in 3D would have been computationally expensive, and the pump characteristics would have to have been done by hand in this case to find out the flow rates. Leveraging the 1D toolset makes this much easier and faster to achieve.